In this video, we're going to take a closer look at our current relationships, and we're going to develop the equations that we use more often in our BJT analysis. So I've copied here just a simple diagram of our NPN transistor from a previous video. Notice we have our three terminals, emitter, base, collector, and I've labeled the three currents as we've seen them in a previous figure. So emitter current on the left, base current on the bottom, and collector current on the right. And so what we can do is we can treat this BJT as a single node. So treat our bipolar junction transistor as a single node, and we can then apply KCL. So applying KCL, we see that our emitter current is the only current leaving, so that has to be equal to all the currents coming in, which is the sum of our collector current plus our base current. And so this is going to be an equation we use quite often. And one thing to keep in mind is that this is true for all operating modes. So whether we're in forward active mode, whether we're in saturation, inverse active, so for all modes, this is going to be true. But as we said, a lot of the times we're working in our forward active mode. So let's look at sort of the special case for forward active mode. So for our forward active mode. And so again, I just want to really emphasize that the equations I'm about to write are only for the forward active mode. So in that forward active mode, like we saw in the previous video, the base and collector currents are linear related. So the base and collector currents are linearly related, so they had that same basic form of some constant times e to the VBE divided by VT. And as did our emitter current, we'll see that we can relate that to our collector current and base current as well. But the equation that we have that relates our base and collector current is that our I sub C is equal to this parameter called beta I sub B. Okay, so I've introduced this new parameter beta, and once we know what beta is, if we have our base current, we just multiply by beta to get our collector current. Again, keeping in mind that this equation is only true in the forward active mode, so it's not true in saturation and inverse active, only in the forward active mode. And so what this beta term is called is our common emitter current gain. And so that'll make sense why we call it that as we look at some different configurations a little later on. So this is our common emitter current gain. And so a couple of things to keep in mind is that this beta is highly dependent on the fabrication. So highly dependent on fabrication. It's also dependent on temperature. So dependent on temperature, but that gets a little more complicated when we get into that type of stuff. So in this class, we're just going to treat it as a constant. So beta for a given device is going to be constant. So of course that's a pretty big idealization, and we're going to come back to that in a different class and see how it changes as some of these parameters are changing, or how we need to accommodate for that change in our circuit design. But for now, we're saying that our beta is just going to be some constant value. And just to give you sort of a rough idea of what some typical values for this beta are, typically it'll be anywhere between 50 and a few hundred. And so we'll see plenty of examples later on where we get to deal with that. So now what we can do is we can combine these two boxed equations here, and we can get a relationship between our emitter and our collector current. So we can say that our emitter current is equal to our collector current plus our base current, but now I'm going to substitute our base current with IC divided by beta. If we rearrange that, what we get is that our IC is equal to beta divided by 1 plus beta times our emitter current. And that's going to be another sort of term we can use, which is our alpha times our IE. And so that should be a lowercase I. And so this alpha parameter is called our common base current gain. And again, as we look at configurations a little later on, it's going to make sense why we call this our common base current gain. And so, of course, as we can see in the equation above, we can relate alpha and beta. We can say alpha is equal to beta over 1 plus beta. Or if we want to go the other way, we can say beta is equal to alpha divided by 1 minus alpha. So although not as important, these two equations can also sometimes be useful. One other thing to note too is that this alpha is, so our alpha is going to be just below 1 or just below unity. And so we can see that if we look at these typical values for beta, 50 to 300. So for instance, if we had a beta value of 100, if we plug that into this equation right here, what we would see is that corresponds to an alpha value of approximately 0.990. And so if we sort of take a big picture look at this, we can see that that means our emitter current is going to be the largest. Of course, we would expect that from here. Our collector current is going to be the second largest, and then our base current is going to be much smaller, 2 orders of magnitude roughly, than our collector current. So hopefully that gives us sort of a better idea of the relationship between these two currents, as well as some useful equations for analyzing our BJT circuits.